All right, in this problem, a rocket travels vertically at a speed of 500 kilometers per hour. The rocket's tracked by a telescope that's down here with an observer located 12 kilometers from the launching pad here. We want to find the rate at which the angle between the telescope and the ground, that's this angle, is increasing 3 minutes after liftoff. Okay, so we're interested in what's going on after 3 minutes. Now this is a general diagram that can be used to set up the problem. So to get an equation relating theta and x, I would use tangent because tangent relates the opposite and the adjacent sides of a triangle. So tangent of theta is equal to x over 12. And you could differentiate both sides of this equation. You could multiply by 12 first, or you could even solve for theta to get theta equals tangent inverse of x over 12, which is a good way to solve this problem simply because if you solve for theta, then you don't have to find additional information for the problem. But I'm going to work it this way. We're going to have 12 tangent theta equals x. We take the derivative with respect to time of both sides. The derivative of tangent of theta is secant squared theta times d theta dt by the chain rule, since theta is a function of time, equals the derivative of x, which is dx dt, so x is also a function of time. Now we are given that the rocket is traveling vertically at a speed of 500 kilometers per hour. That is dx dt. That's the rate at which x is changing, and x is increasing as the problem goes on, as the rocket goes up. Therefore, it is positive 500 kilometers per hour. And we want to solve for d theta dt when t is 3 minutes, or we need to convert to hours so that we don't have any units issues. So that's 1/20th of an hour. So d theta dt is equal to dx dt divided by this. Dx dt is 500, and that's going to be times a 12th, so 500 over 12 times 1 over secant squared theta is the same as cosine squared theta. So we need cosine theta at the moment when t is 3. So in order to find cosine theta, we need the adjacent side and the hypotenuse. But I can't find the hypotenuse without knowing this leg, x, at 3 minutes as well. Well, we can figure out how far the rocket has gone in 3 minutes because we know it's traveling at 500 kilometers per hour. So in 1/20th of an hour, the rocket has traveled a 20th of 500. So in 3 minutes, or 1/20th an hour, the rocket has traveled 500 kilometers per hour for a total of 1/20th of an hour. So my hour units cancel, and I get 500 over 20, which is 50 over 2, which is 25 kilometers. So that is 25 at this particular moment in time. So then we can use Pythagorean theorem to find the opposite, or the hypotenuse of the triangle, which we're going to need in order to find cosine theta. So by the Pythagorean theorem, 12 squared plus 25 squared equals, I'll just call this h for hypotenuse, the hypotenuse squared. So h is equal to the square root of 144 plus 625, which is 769, which, if we take the square root of 769, we get a decimal number. I'm not going to take the time to simplify that radical right now. Instead, let's go ahead and plug this into cosine squared theta. It'll get squared anyways, and the radical will go away, so it's definitely not worth the time to simplify. Okay, so coming down here, we have d theta dt is equal to 500 over 12 times cosine of theta squared. Cosine of theta is the adjacent side over its hypotenuse, so it's going to be 12 over square root of 769, all being squared. There's 12 squared in the numerator divided by 12 in the denominator, leaves me with a single 12 in my numerator over 769 in my denominator. We can leave it like that, or we can approximate. 500 times 12 divided by 769 is approximately 7.8023 The units here are radians, that's the rate of change of theta. Per hour was our units on time.